In this video, I'm going to talk about circular orbits, and we're going to derive an expression that represents how the orbital radius of something in circular orbit is related to the time it takes for one full orbit or its orbital period. When an object is in a circular orbit around a massive planet or star, how much time it takes to orbit once or its orbital period depends on its orbital radius, how far away that circular orbiting object is from the center of that massive thing. In this video, we're going to derive an expression for how these two things are related, the orbital radius and the orbital period. So here's how one question might sound. Develop a symbolic expression that represents the orbital period for an object of mass m, little m, orbiting a planet of mass big M at a constant orbital radius. We'll just use capital R. And we're going to express our final answer in terms of little m, big M, R, and any fundamental constants. So big M is the mass of the planet, little m is the mass of the orbiting thing, big R is the orbital radius or the distance between the center of the planet and the center of the orbiting satellite or object, and capital T represents the total time for one complete orbit or the orbital period. So in order to develop this expression relating big R and T, we need these three equations. If something is in circular motion, we need to use our general circular motion equation. The sum of the forces on the object, which points towards the center, is equal to the mass of the object times its speed squared divided by its orbital radius. And to know the size of the gravitational force on the satellite, which is equal to the sum of the forces, we need Newton's universal law of gravitation. It's the gravitation constant times the mass of the two objects that are pulling on each other, which would be the mass of the planet and the mass of the satellite, divided by the distance between those two masses. So the distance between the center of the planet and the center of the thing orbiting, which is just capital R in this case. And since we want to know something about the period, how much time it takes for one complete orbit, we need to use this version of our constant velocity equation. Velocity is equal to displacement over time. And if we want to know the time for one orbit, we need to know the distance it travels in one orbit, which is just the circumference, which is 2 pi r. So if we have these three equations, we can combine them to figure out how the orbital radius, capital R, is related to the orbital period, capital T. So let's start by using the first and second equation. We start with the second one here. The sum of the forces is equal to mv squared over r. So mv squared over r is on the right-hand side. And what is equal to the sum of the forces on an orbiting satellite or an orbiting object around a planet or a star? It's really just the gravitational attraction that the planet has on that object. So we're going to plug in big G times mass 1 times mass 2 divided by the separation distance squared. And mass 1 we'll just say is capital M, that's the mass of the planet, that's the first object. The second object is the satellite, so we're going to use small m for that. And so we get big G times big M times little m divided by r squared is equal to little m times v squared over r. Before we start simplifying this equation, we need to get the period, the capital T symbol inside of this equation, because we want to find out how capital T is related to capital R. And we can do that by substituting in this equation in place of v, or in this case, v squared. And so on the right-hand side, we get mass times v squared, or the mass of the satellite times 2 pi r over t. And we're going to use capital R because that is the orbital radius. It was given to us that's what capital R represents. So we're going to put in capital R there. And because the distance between the center of the planet and the satellite is also capital R, and that's also the orbital radius, we're just going to replace the lowercase r with capital R's, since that's what was given in the problem. So once we have this equation, now it's all combined. All three starting equations are combined, and we can now simplify to see how the orbital radius, capital R, is related to the orbital period, which is capital T. So the first thing we should do is let's square everything inside of this parentheses. And so inside of the parentheses, we get 2 squared, which is 4, pi squared, and capital R squared. And then we're going to get a t squared in the denominator. And since we're dividing by r, let's just put the t squared and the r together in the denominator. So the right-hand side is little m times 4 pi squared times r squared over r times t squared. And the left side is still the same. Well, now let's start simplifying before we get our final expression. So notice there's a little m in both sides of the equation. So if we divide each side by m, that goes away. The orbital period and how it's related to the orbital radius doesn't depend on the mass of the thing that's actually in orbit, just the mass of the planet, the mass of the thing that's being orbited. Now let's simplify some of these r's. Let's multiply each side of the equation by r, and if we do that, it cancels out one of the r's in the denominator here, and it's going to cancel out the one r in the denominator there. Now that we simplified it, let's see what we're left over with. We're just left over with, on the left side, the universal gravitation constant times the mass of the planet divided by the orbital radius is equal to 4 pi squared times r squared over the period squared. Let's now get r out of the denominator and t squared out of the denominator. So I'm going to multiply each side by r and multiply each side by t squared. And if we do that, we're going to cancel the t squared on the right side, and we're going to get an extra r up here. And then on the left side, it cancels out the r on the left in the denominator, and it gets a t squared up there. And so if we multiply both sides by t squared and multiply by r, on the left side we get the period squared is equal to the universal gravitation constant times big M. On the right side, we get 4 pi squared times r cubed. If we divide each side by g times m, on the left side we just get the square of the period is equal to 4 pi squared divided by big G times big M, all times the radius cubed. And this equation now tells us how the period of orbit, how much time it takes to go around once, is related to the radius of the orbit. The square of the period is proportional to the cube of the orbital radius. And when we look at all this stuff right here in the equation, that's all constant. 4 pi squared, G is the universal gravitation constant. And around a given planet, let's just say that stays the same. We can see the proportionality, like I said, the square of the period is equal to the radius cubed. So if we want to find out what the period is, we can square root both sides, and period is the square root of all of this stuff. Or if we wanted to solve for the needed orbital radius given a period, we could, do some algebra and rearrange and solve to get r equals something. So here's our final symbolic expression. And just to show you, how could we actually use this derived expression to do something useful? Well, we could use this expression pretty simply to determine the mass of our sun, the mass of the star that our planet is orbiting, right? We know that the Earth goes around the sun once every year. That's how we define a year, one trip around the sun. And so we know the period, and we know the approximate distance that the Earth is from the center of the sun. We know its orbital radius. So if we know the period, we know the orbital radius, we can solve for the mass. So if we take this derived equation and we rearrange it for m, we do some algebra, we get that the mass of the planet, or the mass of the thing being orbited, in this case it's the mass of the sun, is equal to 4 pi squared divided by the period squared times the gravitational constant times the radius cubed. And we have all of those accepted values. So the period we said is 1 year, and 1 year's worth of seconds is 31,557,600 seconds. So we're squaring that because we're squaring the period. We get 4 pi squared on the top. The universal gravitation constant, I didn't include units, just the value. It's 6.67 times 10 to the negative 11th. And the approximate orbital radius of the Earth around the sun is 1.496 times 10 to the 11th meters. And we have to cube that orbital radius. So if you crunch all those numbers, this turns out that based on this derived equation, the mass of our sun should be about 1.966 times 10 to the 30th kilograms of mass. That's approximately 330,000 Earths worth of mass. And this is like our theoretically derived mass of the sun. And here's what the accepted value is. It's called the 1 solar mass. It's 1.98847 times 10 to the 30th. And just looking at the two, you can see that our simply derived expression is very close to the accepted mass of the sun. Hope this has been helpful.